Originally, I'm from France, but I'm originally from Algeria. Algeria is the north of Africa. Okay. So, short introduction of myself. I received a bachelor degree in computer science from a university in Algeria. As I told you before, it's North of Africa. After this Bachelor of Technology, I moved to France to prepare a master's degree on artificial intelligence at University of Sorbonne, Paris Nord. After that, yeah, when you do a master, I say, okay, I will continue my research because I say that, okay, I was happy to do research during master, so I decided to not go to the industry and to continue on PhD. Are you hearing me very well, especially there? It's okay? Yeah? So as I told you, I continue on a PhD where I work at the application of machine learning to mobile network at University of Sorbonne University, also in France. At the end of my PhD, I got a postdoctoral teaching and research fellow in a university in the north of Paris, University of Cergy. I would like to ask you, because I'm talking a lot about France, who have been before in Europe? Hands your hand. No what? Okay. No, nobody. Okay. So after my PhD, I said, okay, I did a lot of academia career, so I tried to go to the industry. So after that, I got a position as a research engineer and a project manager at Orange Labs in mobile network operator. In France, I'm also a worldwide. And I got during this period, I get, a diploma, which the name is HDR in France. It is equivalent to tailored professor level from University of Toulouse. And just after that, I moved to academia as full professor at University of Bourgogne, Europe. And since 2017, I'm also the director of one of the labs of this university. Okay? So, just since you told me that nobody was in Europe, I think that nobody was in France also, I will show you where my university is. This is the map of France. This is the map of France. We have here Spain, we have here Belgium, Switzerland, etc., etc. Okay? And my university is is located in one region. In France, we have 8 regions. And the region is Bourgogne-Franche-Comté. Okay? And in Bourgogne-Franche-Comté, the university has 6 campuses. The main campus is in Dijon city. Okay? And myself, I'm in this city, in Nevers. Nevers, it's here, really in the middle, in the center of France. Okay? Some key figures of my university. So, the university is too old, like me. It's more than 300 years old. We have more than 33 students. And the standard in France is to have at least 10% of international students. So we have more than 300 international students. I give here the number of teachers and employees. The university is it's like here. We have different departments, not faculties. With our university, we have a lot of faculties. I'm involved in one of these faculty, which is ISAT, which is an engineering school. 5 years engineering school dedicated to automotive and transport. ISAT Engineering School on Automotive and Transport. With university also we have also 30 research lab. What I mean by research lab, because in our university when you are professor or assistant professor, half of your work is dedicated to the teaching, and the other half is dedicated to the research. And where you would like, so for teaching, I'm teaching in the engineering school ISAT. When I would like to do research, I go to the lab, drive, where I am the director. Short introduction about the lab. So the lab is situated in Nevers. It's about 60 members, teachers, and PhD students, 20 PhD students. A PhD student is a student that continue, after, as I explained before, after the master, you would like to continue for 3 or 4 years to do research in a specific topic. So we are, within our university, we have, within our lab, we have 20 PhD students. And the main word, I will say, in our lab is sustainable mobility, and to attain this sustainable mobility, we are working on materials and comfort, energy, and intelligence. That's why we have 4 teams in our lab. I'm the director. We have the first team, which is dedicated, since we are an engineering school which is specialized on automotive and transport. We have a team dedicated to energy, environment, and propulsion. This is more dedicated to electrical vehicles, to hybrid vehicles, to new biofuels, etc., etc. There is a team which is dedicated to intelligent and connected systems. Personally, I'm part of this team. I have just a slide just after to describe this team. We have another team which is dedicated to sustainability and structural composite, and this team is more dedicated to mechanics, okay, and biomaterials. And the last one is more dedicated to vibration and acoustic. It means that when you are in a car, when you are in a plane, you would like to have comfort, not a lot of noise. So we are doing research to how to reduce the noise within the car or the plane. So my team where I'm involved is SIC, for intelligent and connected systems. So within this team we are leveraging on ICT, information and communication technology, where we apply ICT to different systems, autonomous vehicles, that could be vehicles, real vehicles or drones, Internet of Things, and smart grid, especially the integration of electrical vehicles to the smart grid. We call it vehicle to grid or grid to vehicle. The main idea of the research of this team is to optimize the collection. So we collect data from the different systems, drone, vehicles, things, etc. We try to exchange them, because when we collect the data, we have to exchange them. We have to send them a server. We have to share them with other entities. But we have to share them securely. So we are also talking about cyber security, okay? And after that, when we collect data, we have to process data. If you have data, without doing nothing, it's not normal. And we process data in order to propose different applications. So this optimization is done through the development of algorithms and protocols that are based on analytical modeling, that goes from game theory, multi-objective optimization, dynamic programming, and now we are working a lot on machine learning. And our research goes, as I told you, from analytical modeling to simulation and also experimentation, because within the lab we have also different materials. We have here, for example, an autonomous vehicle, Kona. We have a set of drones, a fleet of drones. Also, we have also a simulator for autonomous vehicles. Okay, this gives you just an overview about who I am and where I'm coming from, okay? If no question on this first part, let's move to my seminar. Yeah, your professor told me that you are comfortable with mathematics. Not really. So, if not really, I tried yesterday to change my presentation to not have a lot of mathematics. But I encourage you to, mathematics is really important for an engineer or master, okay? But in my presentation, I removed a lot of parts for where we have a lot of formula, okay? So if you don't mind, let's start, okay? So my talk is entitled Optimization of Urban Delivery Planning using Reinforcement Learning and Autonomous Drones. Up. Usually, now, if you would like to deliver packages, okay, we have one of the solutions. We have dedicated cars, okay, that goes from warehouses and deliver packages to the clients, okay? And usually this, yeah.
They use resolution so that it can show everything. It's, like some on the top. I know it's full.
It's full, huh? No, it's full. So the current solution, as I told you, is to use dedicated vehicles and usually fuel gas solution. So I would like to ask you, I need answers, okay, to have some interactive session, okay? Is it a good solution, especially when we are talking about sustainable mobility? Is it a good solution to have some actually cars that deliver, especially in Hanoi, for example, where there's a lot of congestions, etc.? Using dedicated vehicles is a good solution or not? Yes? No, why no? Traffic jam. Also, one of the solution is that it's not a good solution because one of the things is delivery time. If we are talking, for example, about big cities like Hanoi, where there is a lot of congestion, as you said, in terms of delivery time, the delivery time will be impacted. Okay. The second one, the maintenance cost, because we are talking about vehicles. Okay. Vehicles that need maintenance. That maintenance it costs. Fuel cost, because usually these cars are using fuel-based gasoline, okay? And gasoline, it has also a price, and there is also an impact on the carbon emission. Higher carbon emission and high traffic jams. So this solution is not really a good solution. Okay. There is another solution. The other one, using drones like Amazon, DHL, etc. The solution already exists. Okay. So we have the drone that deliver the packages to the client. Okay. It's a good solution. Why? Because it's fastest than the solution based on cars. This solution also minimizes the carbon emission because usually it's based on batteries and not fuels. This solution could remove more than 1,000,007 cars from the roads, especially when it's cities where there is a lot of congestions. Drones could reduce the delivery cost per mile from $2 to $0.005 compared to the solution I proposed just before. And it offers a lot of jobs, including IT jobs, network engineering, and the master's student as you are, okay? So it's a good solution, but there is a problem in that. If we are talking about drones, drones are based, as I told before, are based on batteries, okay? And if we are talking about batteries, if we are, for example, in big cities like here in Drone, we can have some problems. If I would like to go to, for example, from PTIT to my hotel, which is 6 kilometers from here, to deliver, for example, to deliver for me a coffee or a gift or something else, it will be a problem, okay? Because the drones are based on battery, okay? This is one of the problems of the solutions based on drones. So one of the solutions for this problem, so just to say, well, when we are doing research, we found in the literature, in the industry solutions, that usually industrials told us, we have a solution, but this solution has certain drawbacks. It's up to us as researchers to find solution to these problems. So they told us there is a problem of battery of the drones, because the drones actually, even the car, because I know that some of you are specialized on electrical vehicles. Just to know, what is I'm not talking about the battery, what is the range of an electrical vehicle? Here, for example, VinFast offer electrical vehicles or no? We have electrical vehicles that are produced by VinFast? Yes? So what is the maximum distance for an electrical vehicles produced by VinFast? I'm curious, I don't know. How much? 100? 400 kilometers? Okay, it's good. So even it's 400 kilometers, the professor said here. You should know that. So the cars, even with the cars we have big batteries, they have their range which is limited. Within the drone, we cannot have big batteries because we have the battery and we have also the package, okay? We cannot add a big batteries, okay? So there is a problem of range. If there is a problem of range, one of the solutions to use dedicated vehicles as a docking station for the drone to the nearest point of delivery. It means that what is the problem of this solution? just to put the drone on the top of a dedicated vehicle, and it's up to the dedicated vehicle to go near to the destination. So we have still the problem of using dedicated vehicles, say carbon emission, etc., etc. This is not a good solution. We still have the same problems as stated in my first slide. The other solution we propose here is to use existing public transportation. It's really important to understand this solution because, yeah, this is the main focus of my presentation. So, our solution is to use, usually when we are in a big city, we have a lot of buses, we have a lot of trams, etc., that are moving on the city. And the idea is to use not dedicated vehicles, but using the bus, using the trams, etc., in order to pick the drone from the warehouse to a destination which is not far from the client. And when we use this solution, why this solution is interesting? This solution is interesting because drones are connected to the mobile network, okay? And they can find information about the traffic, because I have to know if the bus is here or not here. They can collect this information to do in the real time the optimization of the path planning to find the best route to go to the destination. The solution is also good because if I am on the top of one bus, if this bus is stopped, I can move from one bus to another to reach the destination. Okay, this is one of the solutions. We are here talking about autonomous drones, okay? So we have a set of drones. We do not have vehicles. We have a set of drones that are in the warehouse, okay? And these drones have to deliver. We have a solution that is based on dedicated vehicles, and I have a solution that combines drones and transportation systems. And when we propose solution, we have to study the performance, to say, is it interesting or not interesting before deploying the solution. That's what we did at the first time. So, we try to do a comparison between these two solutions, okay? To do the comparison, when we did it by simulation, okay? So to study the performance of a system, there are three ways to do it: analytical modeling, simulation, or real experimentation. You take a drone and you do experimentation. Doing experimentation is complicated. Analytical modeling is also a lot of mathematics, and you don't like mathematics. So we did simulation, okay? To do simulation, but when we did simulation, the idea is to have a realistic simulation. You have to use realistic assumptions. So when you do the realistic assumptions, so the main problem here is to model the energy consumptions. And within the literature, we found that the energy consumption of the drones are not well studied. Because in the literature, there is a model of the energy consumption only when the drone is flying. It's constant. But the energy consumption is different when the drone is taken off. When the drone is taken off, the energy consumption is higher, Okay? Then when the drone is flying, so the energy consumption here is higher than this one. When the drone is landing also, because he has to land to go to the client or to go on the top of the transportation system, the energy consumption of the drone is also different. When the drone is on the top of the bus, it consumes nothing, because the drone is in the top of the bus. It is not flying, it is nothing. Okay? And the same thing, when it goes near to the client, so it takes off, energy consumption, fly, energy consumption, and landing, energy consumption. So we consider all the phases where to go from the source to the destination. And in the literature, they did not consider the 3D environment. They consider, if I would like, for example, to go from this point to another point, they did not consider there is a building. If I would like to go from this point to this point, I cannot go straight away. They have to go through the building and, okay. So in our work, we consider also the 3D environment of the city. So we did simulation. We dedicated simulation tools. So we consider different consumer distribution models in Barcelona. Where is Barcelona? Where is Barcelona? In France? Spain, good. So we examine 10 different consumer distribution. We consider a uniform distribution. This is Barcelona city, okay? And we consider these consumers are distributed uniformly, okay? We consider also a distribution which is normal distribution. What is a normal distribution? A normal distribution, it means that consumers are concentrated in a part of the city and less outside the city. And we consider a cluster distribution. It means that I have 3 clusters, okay? Here there are normal distribution and normal distribution. So we consider different distribution of the customers. We consider also different warehouse position in Barcelona. And here we consider a position on the city center, on the center, on the edge, this is on the city center, on the edge, and outside the city, okay? So when we did simulation, we have to consider all the assumptions. So we consider all the assumptions in terms of consumer distribution, in terms of warehouse position, and also simulation parameters. We consider a drone of speed of 20 meters per second. We consider a payload capacity of 10 kilogram. Simulation area of 100 kilometer square, it's Barcelona city, etc., etc. As I told you before, we consider also the 3D geographical visualization of Barcelona city. And for that, you know OpenStreetMap or no? You have already used it or no? Okay. It's an open source. It's an open source street map. It's like Google, but it's an open source. It gives you the information about the 3D geographical visualization of a city. Okay. So we did simulation. And the first thing, we tried to test is the energy consumption. Okay? And we consider first, as if we consider uniform, normal, and cluster distribution of the customers. Uniform, in the middle we have a normal distribution of the customer, and we have the cluster distribution of the customer. We consider also for each one, we consider also the warehouse position and the edge outside the city and the center of the city. Okay? And we compare three solutions. We compare three solutions. The first one is drone vehicles. This solution, drone vehicles, is the blue one. This one. Drone vehicles is a solution, is the first solution I present. The first solution, we have the drone that goes on the top of the bus, and it's up to the bus to bring it to the final destination. So in terms of energy consumption, there is only two parts. To go from the warehouse to the top of the vehicle. After it consumes nothing, and it consumes also the last part. In terms of energy consumption, is we have a constant energy consumption. Drone only solution. Drone only solution is the one which is in pink. We can see that it is affected by the position of the warehouse and the distribution of the customers in terms of energy consumptions. And it consumes a lot because the solution which is based on drones, it means that it's up to drone to go from the source to the destination by direct flights. If we have a solution with a direct flight, for sure we will consume a lot. Okay? And we can see there is another solution, which is the hybrid solution, this one. The hybrid solution is the solution between two. I use drone sometimes, and sometimes I use the bus. Sometimes I use the drone, and sometimes I use the bus. So we can see that the solution which is hybrid, where I use both the drone and the transportation system, is better in terms of energy consumption. The other thing is the delivery time, because for sure, in term of delivery time, what will be the best solution? Delivery is the drone, because the drone will use direct flight. The drone will arrive first. For sure, it will arrive first. That's why we can see that the drone-based solution, we can see that the drone-based solution is the best in terms of delivery time. The delivery time is small because I have the direct flight. Depending on the distance, that's all. So the delivery time is the smallest one. And the same thing. And we can see that the hybrid system, it's some kind, which is some solution which is in the middle. Okay. So what we can conclude here is it's really important to find a solution which is hybrid, because one solution which is based on drone, it's good in terms of delivery time, but it is not good in terms of energy consumption. Okay, and choosing a solution that is based on both, a flight if there is no bus. If there is a bus, I have to go on the top of the bus. So today, it depends on the time. I will explain two solutions. Okay? One of the solutions is path planning optimization when I consider only one drone. Okay? Within the solution I proposed just now, we say that, okay, the best solution is to use hybrid solutions that combines drone and transportation systems. I will propose a solution for that, okay, to find the best way to go from one point to another. After that, and this solution is based on a machine learning algorithm, which is Q-learning. Who is comfortable with machine learning? Who is comfortable with that? I would like to ask you, who is not comfortable, no comfortable with machine learning? So you are all comfortable with machine learning? So I will ask again my question. Please. Who is comfortable with who is not comfortable with machine learning? Raise your hand if you are not comfortable with machine learning.
I have no experience.
So all the others are comfortable with machine learning? No? Okay. So the other solution, it depends on the time. So the first solution I will talk about, if we have one drone, I would like to find the path to go from the White House to the destination. The other solution is a collaborative. The other solution is a collaborative path planning, and here we will consider a fleet of drones that collaborate together in order to deliver to the clients. So if you are not comfortable, I add some slides on machine learning. What is machine learning? Tips of machine learning. And last part dedicated to reinforcement learning. If you are, if I understand, you are more on robotics, yeah? If you are more on robotics, you should know reinforcement learning, because reinforcement learning is an application, a big application of robotics. So what is machine learning? The definition we found in the literature is this one. It's a subfield of computer science that gives computers the ability to learn without being explicitly programming. And why? Why now? Actually, 5 years ago, all over the world we are talking about machine learning. Machine learning is not new. As I told you before, in 1995, I did my bachelor on artificial intelligence and machine learning. It's not new. Why it is new now? Because it's new, and all over the world we are talking about AI and machine learning, because we have a lot of data. Because when we did machine learning, we need data. And we have computers that are powerful with CPU, GPU, etc. So we can do a lot of things. That's why machine learning now, a lot of persons are working on machine learning. So the idea is to have data. This is machine learning. We have data. We have to train our system on the data. When we train data, we have to answer questions. And we ask the system to answer questions, to predict or to calculate something. Okay? So this is traditional programming. What are the programming languages you know? You know C, C++. That's all. MATLAB, Python. If you know Python, you know machine learning, no? A little bit. So, traditional programming, when you program, you have the data, you have your program, you put it on the computer, and the computer produces a solution. Okay? If you have to calculate the sum of A plus B, 5 plus 2, you have the program, you give the system, I would like to give me the solution of 5 plus 2. 5 plus 2 are the data, and the system will compute and give you the production. It's 7. 5 plus 2 is equal to 7. This is traditional programming. Machine learning is different. You do not have to program. That's good, no? Nothing to program. You have data, you have a lot of data, and for each data you have a prediction. You know, for example, you know what you would like that your system gives, okay? You give it to the computer, and it's the computer to give you the model, a black box. And you have just to use after that this black box to predict also to calculate things. Okay? It's really important to, is it clear now the definition of machine learning? So it's different from what you did before. So when we talk about machine learning, we talk about different kinds, different types of machine learning. We have supervised machine learning. We have unsupervised, it's not, and we have reinforcement learning. Let's first concentrate on the first one. Supervised learning, it's learning that learn from examples whose outcomes is known. So the goal is to find a function that maps x to compute y. Okay? The idea is to compute a function f. Okay? If I give to this function x, it will give me y. Okay? For example, if we have to calculate 3 factorial. 3 factorial, you have to calculate it either by programming, it's equal to 1 plus 2, 1 multiplied by 2 multiplied by 3, it is equal to 6. The idea of the machine learning is to learn it. Okay? I give the system saying, okay, factorial of 3 is equal to 6. I give him also the information, if x equal to 4, the factorial of 4 is equal to 24. Okay? I give it a set of example, x, the input, and the corresponding output, and it's up to the system to calculate the function f. Okay? The algorithms make prediction on the training data. So we have a training data that I give to the systems, which are corrected based on correct answer, and this interactive process continues until the satisfactory level of performance is reached. So you can understand that, yeah, if I would like the system to learn this function f, I need a lot of data. So if I would like to calculate factorial of a number, I have to give the system different examples if I would like that the system learns. One of the examples, is it a car or a truck? I give the system pictures of a car or a truck. So I give him a picture of a car, a VinFast car, a VinTAT. I tell him that this is a car, this is not a car, this is a car, this is not a car. It is also used to I give him also an example of emails. I tell him that I received this email is a spam, this one is not a spam, this is spam, etc., etc. I also predict car price. I give him an example. This car, this price has an A, it's a new car. The price is this one. This one is, the brand is this one, and the one, and it's up to the system to predict price, consumption, mileage, etc. So to summarize, supervised learning, it means that I have examples. Okay, I give the system example, and it's up to the system to learn by the examples I give. So, in this example, what are the difference? What are the difference between the three examples? Do you have an idea? I will give you the answer. Okay. For this one and this one, for this one is just to say, is it a car or is it a truck? Just to say what is the, and this one is just to check, is it a spam or is it not a spam? So it's some kind of, I will say, class. It's some kind of class. I have just to know what is the class. Okay? I would like the system to learn what is the class. Okay? And for this one, that is the class? No. I would like the system to give me a value, a price, a consumption, etc., etc. This is the difference. So the difference between these two examples, this do give me the class, and this one give me the value. That's why supervised learning, we have two kinds of supervised learning. We have classification and regression. So when we talk about supervised learning, we talk about classification and regression. Classifications, it means, as I explained just now. So the output of the system, of my model, based on data, is discrete value, representing a category. Is it a car? Is it a truck? Is it a spam? Is it not a spam? So I give here, for example, an example of classifications. So I give the system a set of pictures, okay, and I tell him this is a cat, this is a dog, this is a cat, this is a dog. I give him a lot of input data, and it's up to the system to classify, okay, to classify what are the dogs and what are the cats based on different features. I will talk about features just after. So this is classification. The other method is regression. Regression, so the output, it's a continuous value. It's not a class. It's not a discrete value. False, true, truck, no truck, etc. Here, I have to calculate a continuous value. For example, the price, speed, consumption, etc., etc. I give here, for example, an example. I give the system a set of houses. I tell him, this house has been sold with this price. This one with this price. This one with this price. Ta 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 ta. Okay. The system learns, and after that, he will learn a function, and based on this function, I can ask him after, if I have a new house, at what price I can sell it. Okay? So, classification. I give here an example. So, how classification works. So, the idea is to give the system, as I told you before when we talk about machine learning, supervised learning, I need data. I need also the output. I have to say the system that I give him this picture, and for this cat, for example, it has a size which is equal to that. It has a weight equal to that, and it is in French, chat, it's cat. So that. This one is a chien. Chien is a dog. Sorry, I didn't translate. This one is a cat. This one is a dog, and this one is a dog. I give him a lot of input data. Okay. And after that, so I define the classes, cat and dog. I defined the features, which are here, size and weight. Okay. And I label the data. I tell him this photo is a cat, this one is a dog, etc., etc. And it's up to the system to find the model. It's some kind of line, okay, that will split the system, our example, in two parts. Here we are talking about two classes. We have to split my data in two classes, the class of the dogs and the class of the cats, based on the features I identified, size and weight. Based on the size and weight, it's up to the system to learn this model. Okay? And why it's learned, the system, I told you, yeah, when we are talking about machine learning, there is a training phase. The training phase, it learns the model, okay? And after I have my model, I have to use it. I give the system a new animal. I give the size is this one and the weight is this one. I ask the system, is it the cat or the dog? So the system learns already the model, and based on the model, it identifies it as this is the size and this is the weight. It considers it as a dog. Is it clear? Okay. Now, regulation. We say when we talk about machine learning, we have classification. We have to classify which class, cat, dog, car, truck. Regulation is another type of machine learning which is dedicated to find a continuous value. The same thing, we are talking about supervised learning, and we have to learn a function. So here I gave the system an example. For example, present a set of houses, and in terms of superficie, this is the feature. I consider only the superficie of the living space. The living space of this home is 92, and the price is this one. The second, I give the system different sizes of the house, and for different size, the house was sold at this price. And the same thing, it's up to the system to learn the model. It learns in terms of living space, the size of the house. It learns this line, this model, okay, that says that can be used after for the prediction. So after that, if the model is learned after the training phase, I will ask the system, for example, if I have a house, okay, I have a house, the living area is 150 meters square, I would like to give me the price. So I will use this system, and the system will tell me that you can sell it at 288, okay? It's clear, supervised learning. Supervised learning, just to mind, supervised learning, it means that I have data which is labeled, okay? It's like a professor. It's a professor to learn the system. Okay, this is good or not good, this is good or not good. It's a system to learn after. Unsupervised learning, unsupervised learning, we have a lot of data. And it's up to the system to discover hidden structures in data without providing expected results in advance. There is no professor that say good car, not car, good, not good, etc., etc. I give only the system a lot of data. It is up to the system of it to learn something from this data. An example. I have some photos and I want to sort them in a set of groups. So I give the system a set of the photos and it's up to the system to group them based on some features. Okay. I give some photos also of car models and it's up to the system to group them in terms of power, weight, etc., etc. And for unsupervised learning, the same thing. We have two kinds. We have clustering and association. We will talk today only on clustering. Clustering works, how it is a definition, is to group data points based on their similarities, okay? I give the data to the system, and it's up to the system to group, for example, all the customers, for example. I have the habits of the customers, and it's up to the system to group customers based on their, for example, buying habits, and based on that, I will cluster. I will have 10 clusters based on their buying habits. Association, I will give only an example of that. Association is discovering a relationship between the attributes of the points of the data I give to the systems. So for example, I give the data, and it's up to the system, for example, to know people who buy a new house also tend to buy new furniture. The system will give me this information. Okay? So there is no professor as supervised learning to say that. It's up to the system, based on the data, he has to know, for example, to know what are the interesting relations or group of the system I would like to know. Up. Up. No need. The last one is, we talk about supervised. Supervised, I need data, I need the label. Unsupervised, I need only data. It's up to the system to learn how can I have interesting information from this data. And the other machine learning is reinforcement learning. Reinforcement learning is really important for you. Reinforcement learning is a machine learning method in which an agent learns to make decisions by interaction with an environment. So we have an agent here, and we have an environment. Based on the state of the environment, I have to do an action. And when I do an action, I will receive a reward from the environment. It's really important applications, especially for robotics. When we have a robot, for example, who wants to navigate, Okay? I know, for example, there is an obstacle behind the robots. It's up, the state is the fact that there is an obstacle. The action is to go behind. One of the actions is to go behind. If I go to the obstacle, what happens? Yeah, so the reward will be not good. If I try to go through the obstacle, so the other action is to find another route, that's another action, and this action is better. This is reinforcement learning. So I have to know it's an interaction between the agent, okay, and the environment, okay. Based on the state, I have to do an action, and when I do an action, I will receive a reward. So, why machine learning is important? Ability to learn from data surpass the performance of traditional models. For example, before, if I would like to recognize, if I would like to develop a program that is capable to recognize objects in a photo, I have to do a lot of mathematics to do it. Okay? This is what was done before. Actually, with machine learning, no need. It's up to the system to learn without a lot of mathematics. I know you are comfortable with that. So machine learning is your solution. Okay? Let's go to reinforcement learning because, yeah, it is a big part of my seminar. Suppose that we have a robot. That it's up to the robot, which is in a maze, and it's up to the robot to find the route to the exit. What is the exit? I think that, yeah, it's, you find it in journal papers, a lot of things, a lot of games where you have to find the exit. My kids love that. This is the exit. This is the right path. Do you think, my question, do you think, to find a solution, do you think we need machine learning here? No. Are you comfortable with graph theory? Have you, no? No? I'm sure, like my student, when I ask them that if they learn something, they say no. And usually they already did. So one of the solutions is model-based solutions. Model-based solution, it's I can model my system, I can model it as a graph. This system, I can model it as a graph. This is the exit. So if I would like to find a solution, there is some existing solution that exists in graph theory. For example, Dijkstra, you know it? You told me no before. Bellman-Ford, stars. This is what I mean by graph theory. So there exists some algorithms that if I give the graph to the algorithm, it finds the best route. And it told me this is the best route to the exit. Go there, go there, there. This is the best route, and you find the solution. Okay? So why I'm talking about? So what happened? So what happened if, for example, during moving of the robots, we have this obstacle? Do you think that the robot will find the exit or no, using this model? Is there a route from, this is 2, 4, to 3, 4. 2, 4, 3, 4. It does not exist anymore. It's closed. So is there a route to the exit? No. So that's why model-based that are based, for example, on graph theory are good if the environment is not dynamic. If the environment is dynamic, the model-based cannot be used. I think usually when in robotic you use also dynamic programming. Do you already use dynamic programming? No. It's related. It's related also to graph theory. Okay. So it not works. So reinforcement learning becomes relevant. Okay. I'm not telling you that you have to use learning for all the problems. Okay. For example, if you have a maze, does not change. Don't use reinforcement learning. Use graph theory. Graph theory is better. Okay, but it's faster. But when your environment is uncertain or changing, model-based does not work. You have to use machine learning, especially reinforcement learning. So usually when we talk about reinforcement learning, we talk about Markov decision process modeling. So we model the problem with a set of states, a set of actions, and a set of rewards. So for the example of the base, so we model the system on 25 states. A1, B1, A2, A3, these are all the states where the robot can be. Okay, we have 25 states. Okay, we model our environment with 25 states. What are the actions? The action is to go up, down, right, and left. Okay, and we define a reward. A reward, as I told you, is when I receive the state, I do an action, I will receive a reward. And we suppose the agent changes its state, so it moves from one state to another, and we assign a score of -1 each time the robot moves from one state to another. You will tell me why to give him a negative reward when it moves. Don't worry, the machine will not be sad if I give him a reward of -1. Why? Because the robot will learn that it's better to have a reward of -10 than having a reward of -15. It's up to the system to learn, it has to maximize the reward. So it knows that, I will give a result of -1, -1, -1. I know, okay, I have to find I have to find something, a solution that gives me the best reward. So the best reward is -10 and not -15. Okay? So the idea of reinforcement learning is to learn a function as any machine learning. We call it policy. Policy that when I am in state S, when I am in state somewhere there, it's up to the reinforcement learning to tell me what is the best action I have to choose. Up, right, down, etc. This is the role of reinforcement learning. How it works now. So, as I told you, just a summary. So, when we are talking about machine learning, as I told you, we are talking about Markov decision process modeling. So we define a set of states. You have to define first the set of states in general. After, you have to define the set of actions. And you have to define the set of rewards. Every time you go from one state to another, you have to define what is the reward. And it's up to the agent to learn a policy that maximizes the set of the rewards that will be learned all the time. Okay? One of the main known algorithm in reinforcement learning is Q learning. Q learning is time difference method that combines the advantage of dynamic programming and Monte Carlo. I will not go in depth on that. So the Q learning is reinforcement learning. So we have to define states, actions, and rewards. And the main objective is to learn a function Q that takes in input S and an action A and predicts a final score, okay, that we can expect to obtain everything goes well afterwards. It means that if I am in this state, I take this action, I will have this score, okay? For example, if I am here, I will go to the north, after, left, south, tap. The system tells me that your final score will be equal to -9. Okay? Because, yeah. Every time I told you I move, I have to, the reward is -1. -1, -2, -3, -4, -5, -6, -7, -8, and -9. Okay? Now, if I go to the left, what is the Q value? -1, I'm stopped. I have to return back. -2, tap. What will be the value? It will be equal to -11. I have to do that, okay? And the system knows, for example, that if he is, for example, in this state, it's not a good idea to go to the left. Because, yeah, the Q value is -11, and there is a better Q value, which is -9. So, the problem here, it works, but how to learn this function? If we have this function, our system will work very well, but how to learn this function? It learns by exploring. It's up to the robot to explore all its environment by moving randomly. It's up to the system to move. For example, when he is here, he can move on all the directions. And we got a reward, -27 here, -22, -15. It has to do all the combination. Okay? And after that, he has to set a function. Usually we represent it as a table, a Q table. Okay? We are here the states, and we have here the actions. When we are in this state and we go to the up, we will have this reward. We go to the left, we have this reward. Okay? And the idea is to learn this function. But every time, as I told you, every time the robot moves, it has to calculate these values. how to calculate them? We use a Bellman equation. If you are comfortable with Bellman-Ford, which is used in graph theory, it's similar. Bellman equations. So we use this equation, which is related to the new value. This is the reward I receive directly when I do an action, the action A. And this is a discount factor. And here the expected reward when we go to the new state S prime. Okay? It's like an analogy here. For example, I give you the example here. When we are in a road, Bellman-Ford is this. If you not remember what is Bellman-Ford equation, Bellman-Ford says, okay, for example, turning left give you, if for example the destination is here, if you would like to go here, okay? If you go to the left, immediate reward will be, if we consider only the distance, we will have good reward, okay? But when we come here, there will be a congestion. If you have a congestion, you will reach the destination maybe 1 hour after, okay? And if you go to the right, maybe you will find another route and reach the destination before. Bellman-Ford, it takes also, in fact, what happens after your action, okay? Up. I will not talk about it. Yeah. Usually, I told you, yeah, Q learning represents usually the table as a table. The states and the actions, okay? But when we are in an environment where there are a lot of states or continuous states, and we have, for example, continuous actions, what will be the size of the table? Huge. Okay, that's why usually there is another solutions which is called deep Q learning. Deep Q learning, it means that rather than representing it in a table, I will represent it by a neural network. Okay, and with this neural network, when I give it, it's the same thing, huh? The same thing. This one and this one is the same. When I give as input the state, it will calculate and tell me, okay, the Q value of action 1, the Q value of action 2, the Q value of action 3, and I will take the action with the highest value to go to the left or the right, etc., etc. This part I will not talk about. Let's move now to, I'm not sure we will have time to talk about the two proposals, but I will take about maybe the first proposal, which is path planning, optimization for one drone, okay? So we say that, remember what we said before, we are talking about a system which is composed of drone and transportation systems, okay? And I would like to find the best route to go from the warehouse to the client through different phases. Flying, after on the top of the transport, after flying, etc., etc., until I reach the destination. And I propose, we are talking about only one drone, and the idea is to find the best path. And we propose to use Q learning. Why we are using Q learning? Can someone tell me why we are using reinforcement learning with this problem? If you understand my first part of my lecture dedicated to reinforcement learning, you have the answer. Is our system static or dynamic? Could you use graph theory or no? No. Why? The environment is changing. Because we are dealing on the bus. Maybe we have to put on the top of the bus. Maybe I can miss the bus. Okay? So the environment is changing. I cannot use a graph theory. That's why we choose Q learning. This is what we talked just before, so if it's clear for everyone, okay? I give here an example. I give an example what I mean. The environment is changing. Suppose that we have to go from the warehouse to the client. If I consider these are, for example, the different stops of the bus, okay? I can say, okay, I will use at time t equal to 0. It gives me, this is the best route. Okay? At t equal to 0, it's okay. But the drone will change. It will, at time 0, it will be there. At time t equal to 1, it will be there. At time is t equal to 2, it arrives here. Okay? But there is no path that go from here to here. The bus, we missed the bus. There is no bus that can bring from S4 to S7. So what happens? So the initial path that was calculated using a model base or graph base is outdated. Okay, that's why we are using Q learning. Here we are talking about shortest path. We are not looking for the shortest path. We are looking for the earliest arrival path. Okay? Shortest path in terms of distance or shortest path in terms of time. Here we are talking about what is the most important in delivery is to deliver as quick as possible. Okay? That's why we are dealing with the earliest arrival path. Suppose that, here for an example, suppose that we consider that for going to one point to another, it takes 1 second. And the departure of the bus at S4 to S7 is scheduled at 5 seconds. And from S4 to S5 is scheduled at 3 seconds. Okay? If we consider only the shortest path, if we consider the shortest path, for sure this will be the best path. If we consider this best path, so the best path length is 4, okay? 1, 2, 3, 4. But the drone will arrive at time 7 seconds. Okay? Here, if we consider the earliest arrival path, the path length is 5. It's so longer than 4. But the drones arrive at 4 because the bus depart at 3 here to go to 5. Okay? That's why we consider the earliest path arrival. In our work, we consider also energy consumption. Okay? The same thing, as an example of, suppose that we have, for example, the energy, these are the path, the energy passed when this color, it costs 1. It means that the drone is flying. Okay? And the energy cost of the red color is 0. It means that the drone is on the top of the bus. Okay? So here we are considering energy consumption because if we consider this route, the energy consumption of the path will be equal to 2. If we consider this path, the energy consumption will be equal to 1 because the drone will use almost the bus to go to the destination. So here we would like to find the best route that consider time and energy. So to model the problem, we model it as graph, okay? The graph with the set of V, E, the edges. So V are the set of stops, warehouses, and customers. All the nodes here are stops, warehouse, and customer that constitute our graph. E, the edge is the relation between two nodes, okay? And the edges represent E represents the links between the pair nodes, where L could be the path between two nodes, could be L0. L0, it means direct flights. Or I have to use one of the public transportation line. Line 1, line 2, okay? And we have also the time, the journey trips of each line. For each line, for each line of bus, we have a timeline. We have a bus that goes at 10 a.m., 10 a.m. 15, 10 a.m. 20, etc. This is the journey trips of each time that we consider that are already known. It's better, thank you. And here we consider, as in my first presentation, we consider the energy consumption under two phases, hovering and flying. Flying when I am going from one point to another, and hovering when I am waiting for the bus, okay? So I consider the energy consumption only on these two phases. So the idea, as I told you before, I would like to find the best route that consider two metrics. I would like to reduce the early arrival time, and also to reduce what? The energy consumption of the drone. So this part, this is the waiting time, and this is the travel time, okay? The waiting time is the arrival time minus the departure time, okay? And this is the traversal time when the drone is flying. When the drone is flying, this traversal time, I multiply it by the energy of flying. And here, the arrival time to the stations and the departure time, this is the waiting time, I multiply it by the energy of hovering, waiting for the bus that arrives, okay? So this formula gives me the energy consumption of the drone when he is come from another point to another, where I consider hovering and also flying. So for our graph that we consider that is composed of set of nodes, and which node is linked with either a direct flight or a line of bus, okay, I would like to find, the problem is to find the best consecutive trips from among all the trips in real time that consider first the energy consumption and the time. I would like to minimize the time of arrival and the energy consumption. And the idea is to find, when I am here, I would like to know what will be the best consecutive path I would like to go, because there are a lot of ones. There is also these ones, there are also these ones, and within only one line, for example, I have this one, and maybe if I miss the first bus, I have to hover to take the second. So there is a multitude of paths. We are considering a lot of buses, and for each bus we are considering what? Different timeline of the bus. So there are different solutions to go from 1A to 1B, okay? And using graph theory, we cannot do it. That's why machine learning and Q-learning is the best solution. Since machine learning is the best solution, when we use machine learning, especially Q-learning, we talk about the Q-learning in the first part of my lecture. When we use the reinforcement learning, we have to model the problem as Markov decision process. We have to define states, actions, and rewards. Okay? How to define actions? The actions is the graph node plus the time. What time I am, okay? The different actions are LOT, LT. L, it means I use what I have to use. I have to fly, or I have to use one line, okay? And which line? So L, so it is either public transportation line. L0 is, it means that I will not use the transportation, I will use a direct flight, okay? And T is specific route or air route. It means that what I am, and if there is a bus or there is not a bus. If I will take the bus at this moment, or I have to wait, for example, for the other line, which is better, okay? So the state are there, the action are defined. What is missing? We have the state, we have the action, the reward, yeah. This is the reward. And the reward, as I told you before, a reward is something related to what? Without saying what I put here, it's related to time, early time, and energy. So it is something which is related. I would like to minimize the time and the energy. I will not go in depth in the formula. I know you love formulas. So it's just to say that the reward is more related to something I would like to minimize, which is the early arrival time and the energy. So, as in the beginning, the first part of my lecture, if we propose something, we have to study its performance. To say, okay, I propose something, but I would like to know if my system is good or not. Analytical modeling, simulation, or experimentation. We prefer to do simulation. To do simulation, we try to do with this network. This is the source, the warehouse, and this is the client. And we have here different bus stop, and we have different bus lines, okay? We have the different lines, for example, different line of bus, L0, L1, T, okay? And these are the arrival time, the time what they, with what is put in bracket is the variance. It means it could be 13, it could be 14, it could be 15, etc. Okay, to add some kind of randomness. Okay. These are the departure lengths of each line. And when we did simulation, when a big problem of machine learning, I didn't talk about it before, is the convergence. Because I told you before, when we did machine learning, even supervised reinforcement learning or unsupervised, we give data, but depending of the training phase could take a lot of time to be sure that your model is converging. Okay, so within our the problem is bigger within reinforcement learning. One of big problem of reinforcement learning is the convergence. That's why there are a lot of solutions on that. We did not have time to talk about it this morning, but I hope if you are interested on that, go in depth. Yeah, because I give you the basic concept of reinforcement learning. If you go, you can find some other solutions that adapt, enhance reinforcement learning in order to be more efficient. So in terms of convergence, we can see that our system converges after mid-epoch. So it's stable. When it is stable, it means, okay, we are learning, we have a stable system. No need to go more because we have a system that is converging. We also found that using our system, 100 success rate in parcel delivery. Within our system, we did a lot of simulation, and delivery was 100% of success compared to the other solution. We compare our solution, which is based on co-learning, with another solution, which is immediate reward-based. Immediate reward-based, it means I will consider only the immediate reward. I will not consider what happens in the future. Okay? And this is what is good in reinforcement learning. You remember Bellman-Ford? Bellman-Ford, it means that I have to learn also what happened after. It's not only the immediate reward. We can see in terms of energy consumption here, co-learning is better. It depends on the extent of the departure of the drone. 0, 1, we can see that our solution, which is based on co-learning, is better than the other solution. In terms of also of traversal time, we can see that our solution, co-learning, is also better than the other solution based on immediate rewards. I'm not sure we have time to go to the other solution, which is based. I will talk about it briefly, and I will stop just after. So here, what we propose. The first thing, we start talking about what is machine learning, and we say that there are different kinds: supervised, unsupervised, and reinforcement learning. Okay, there are other tips. Okay, it's up to you to find them. There are self-supervised, etc. It's up to you if you would like to go in depth on this topic. It's up to you to go in depth. It's your responsibility. After that, we talk about the problem of drones delivery. When we are talking about smart cities and sustainable mobility, drones could be one of the solutions, because actual solutions that are based on dedicated cars, gasoline cars, are not good in terms of carbon emission, etc., especially in big cities like in Hanoi. Another solution that is based on the drone is a good solution. but there is a problem of battery. That's why we propose a solution which is hybrid, that use the drones and transportation systems. We found that this solution is good, which is hybrid in terms of traversal time and also in terms of energy consumption. We formulate after the problem because we are in an environment which is dynamic. Since we are dealing in bus, and the bus, when we are in the city, the bus we have different lines to go from one point to another. If we would like, for example, to go to my hotel, maybe I have to take 2 or 3 buses if we not take a Grab, okay? If we take a bus, I have to take different connections. It's the same thing for the drone, okay? And it is related to time departure of the drone, of the bus, and the bus also have a problem. Also, if there is a congestion, maybe if it is supposed that it comes at 10 a.m., maybe it will come at 10 a.m. 10, okay, past 10, okay. So we have an environment which is dynamic. Since we are in an environment which is dynamic, it's not possible to use model-based solutions like graph theory. That's why we decided to use reinforcement learning, because our system is dynamic, is not static. Okay? We defined our problem as a Markov decision process. We defined the states, we defined the actions, and we defined the rewards. We did simulations, and we say that our solution is good if you are dealing with a drone that would like to, only one drone that would like to deliver from one warehouse to a client. The problem is we define Q-learning with, I give you just the problem, I will stop just after, okay? So if we have one drone that would like to deliver from one warehouse to another client, we will have a Q table. Remember what is a Q table? The Q table is this one that tell me if I am in this state, it's better to get this action because this action has the highest value. Okay? This is Q learning. So now if we have another client, it means within the warehouse I should have another Q table related to this client. If I have a lot of clients, what happens? I will have a Q table for each client. Is it a good solution? No. So one of the solutions we propose is, you have the solution. I already talked about it. One of the solutions is to use deep Q learning to represent the Q table by a neural network. Okay? The other this is what I put here. There is a problem of scalability, and to resolve this problem, we use deep Q learning. The other problem we got, I'm talking about just the problem, I will not talk about the solution. The other problem we got, when we are, for example, 2 companies of delivery, okay? The first company is that has a set of drones, and the other company is that has a set of drones also. What happens? We have, for example, a possible overlap collaborations between the 2 companies, okay? And each company has it should learn by itself, okay? But it is not interesting to have some coordination between them in order to learn more quickly. It's interesting. But if they would like to learn each other, with each other, to help each other, I would like to learn, but I don't want to give you the information about my clients. but the affirmation are private. Okay? What will be the solution? If we would like to learn without giving the information, all the information, all the data, one of the solutions that exists in machine learning is so here we have a competing logistic companies. We have a privacy concerns because these companies would like to help each other, but they don't want to share the information that they create. One of the solutions is federated learning. So this is the global view of our solution, and we stop just after. So to resolve the problem of scalability, rather than using key tables, we prefer to use neural network to present the key tables, and to have a problem of collaborating between competitive companies, we use federated learning. What is federated learning is just in summary, what is a federated learning? I'm a company, you are a second company, and you are the third company, and you have your own customers. So the idea is, if the best way is to give all the data to a third party, and you give the data to the third party, and you give the data to the third party, and it's up to third party to learn and give us the information about the model. It's not a good solution because I have to share my data. The solution of federated learning is that, okay, I will learn in my own data, you will learn in your own data, you will learn in your own data, you will not share your data, you will share only the model you learn. You will share it with the others, I will share it, you will share it. The system will learn based on the model and not the real data. And after that, it will give me an update of the model. This is the main concept of federated learning. So, ladies and gentlemen, I hope you, since I know that yesterday it took me a long time because you told me that you are not comfortable with machine learning. I did a presentation of machine learning. I hope it was beneficial for you. Okay? I didn't talk a lot about mathematics also. I hope that it was beneficial. It was a good introduction. What is, if we would like to do research after your master, this is the right methodology. You find the problem, you propose a solution, you consider not simple solution, you consider, for sure you have to take assumptions. When you take assumption, the realistic assumption, and after that you have to study the performance, either by analytical model, simulation, or the best way is experimentation. But experimentation, it's in terms of logistics, it's a little bit complicated. So I propose to stop here, and let's move to if you have questions or anything else.